So today is going to be the last lecture on optimization, and I'm going to spend pretty much all the time on these two things. Constrained optimization, all of these are nonlinear optimization. I'll first talk about why nonlinear optimization makes things hard, what makes it difficult. Talk about two kinds of nonlinear optimization. Again, this is a very large field. There are many, many things going on, and I can't discuss everything. I'm just going to give you a sort of taste of things. One is constrained optimization, where we have essentially mathematically nice functions that are continuous, twice differentiable, and defined over the entire domain. In this case, R to the n, the entire real hyperspace. And that makes things nice. And then we can use two kinds of techniques, the Lagrangian or what are called Kkt or Kkt Conditions. So talk about these two. And then when we don't have something that's nice, which is actually most of the real world, then we have to use heuristic optimization. And the most successful one of these actually is hill climbing. This turns out to be something that works almost all the time. I'll talk about hill climbing in some detail, some variants of hill climbing, and then give you just a brief outline of genetic algorithms. There are many, many other heuristic algorithms out there, probably 10, 20 more that I want to just mention, but I won't get into in any detail. But we'll start again with the first thing, which is just nonlinear optimization. So why is nonlinear optimization hard? And let me try and give you an intuitive understanding of why linear optimization is easy. So in linear optimization, generally speaking, we have some function, y equals fx, okay, and these are vectors. This is the objective function. Maybe I should just call it O equals fx. And the nice thing is that because f is linear, okay, a small change in a component of x causes a small change in the optimal value over here, in the objective function. So if I think about the polytope that we discussed, in linear programming, there's some kind of hyperdimensional thing. As I walk along some edge of this polytope, all right, essentially what I'm doing is when I walk along the edge is to change some number of elements of this vector, by small increments. And as I walk along it, what's happening is that the objective function is also going to increase linearly. So as I walk along this, the objective function goes smoothly, linearly, which means it always increases or decreases. Okay, that's basically it. It's linear. There's not a whole lot of stuff going on. It's some combination of a1, whatever, x1 plus a2, x2, etc. So if I change some number of these an's in some fashion, which is just a vector along along this hyper edge, the output is going to be changing by some small increment. It's not going to change its sign. It's not going to go up, down. It's either going to keep going up or keep going down, which means that we run out of room in some sense at the edge of the polytope, at the vertex, and that becomes a candidate for an optimal point. And if that's not the optimal point, we find some other edge, kind of move along that part, and you come to the edge over here. So linearity allows us to do this hopping from vertex to vertex of the polytope in the case of linear programming. Of course, in the case of integer linear programming, we can't do that because, again, we have to make jumps. We can't go here. We have to go from here to here to here. And when you make these jumps, of course, things go crazy because the objective function can change. Similar problem arises with nonlinear optimization, where what happens is that when you have some kind of hyper edge, if you want to think of it that way, as we move along, actually what will happen is that the objective function can go up and it can go down. It can go up and down many times, okay, depending on how it's defined. And so we don't have this nice property that the optimal value lies at a vertex of the polytope, okay. It can be anywhere, okay. So we're kind of stuck. And this fundamentally is the reason why we can't just use linear programming for nonlinear systems. Nonlinear systems tend to have a completely different type of approach altogether. So let me give you sort of intuitively one approach that we know how it works. We've done this probably in high school calculus, and that's to find the maximum of some function of one variable. So I have some function for x, I have fx, And the optimization problem here is, I have some function defined in some fashion, and I want to find the minimum or the maximum value, right? This is a classic problem in real analysis. What do? We basically take the derivative of fx. If f dash x is defined, we set f dash x equals 0, and that gives us all the points where the slope is not changing. And Fermat's theorem tells us that these points, including this one here, all the points where the slope is 0 are the candidate values for the minima or the maxima of this function. And then we take the second derivative, and that tells us whether it's actually a minimum or a maximum. So this is sort of straightforward elementary calculus. So can we use this technique? Can we use this approach from calculus to find the maximum value? Why not, right? So in the first class of techniques, what we do is to generalize from the classic real analysis to what's called Lagrangian optimization. And so Lagrangian optimization, so let me so in Lagrangian optimization, what we have is some function f that we want to find you want to find the value of x such that fx is maximized. So find given fx, find x star such that fx is maximized. Now, if that was all that we had to do, we would just use Fermat's theorem. We would just assuming that f is twice differentiable and continuous, right? We need those two things, so f is mathematically nice. If it's twice differentiable continuous over the domain, then we just finding this is easy, right? We just do it, we plug and chug. But we want to do, Lagrangian says given fx and constraint gx, okay? So these are again vectors. Find x star such that fx is maximized subject to gx equals c. So gx is then the constraint that says you must have gx equals c while simultaneously trying to maximize fx. Okay, so this is where it becomes a little bit more interesting. If you're not giving the constraint, then it's just straightforward. It's just real analysis. It's no big deal. So what I'm going to consider now, and this is the basis, as I said, of Lagrangian optimization, is given fx and a constraint gx, find the value of x star such that fx is maximized and gx is equal to c. Okay? So any questions about the setup over here? Now it turns out that this type of constraint function and this type of function is very, very common in game theory. So when you study game theory, pretty much every game will be cast in the form of find the value of x such that this f is nice, okay, mathematically nice, subject to this, and pretty much all the theorems in game theory fall out of this pretty naturally. So it's a useful thing to have, again, in your tool belt as you start approaching these kinds of problems. So how do we solve this? And there are kind of two approaches to doing it. One approach of doing it is sort of a cookbook formula, which I'll come to. But before I get to the cookbook formula, I want to tell you the intuitive understanding of how it works. Then I'll show you the cookbook formula, and then we'll do an example with the cookbook to show you how that works. So we'll start with just a two-dimensional case, just because it's easier. And so in this two-dimensional case, we have some function f, x, y, and g of x, y. And we want to maximize, we want to find the values of x and y. Again, now x and y become scalars, and gxy equals c is my constraint. Okay, that's my constraint over there. Okay. Now, the technique, the thing you need to remember now is a notion called a contour or a level set. And a level set, to go back to this picture over here, I sort of draw a line like this, and then I have these 2 points. these 2 points have the same value of fx. So it's called a level set for that level. Here is another level set. Here's a level set with 4 elements, and so on. I can kind of draw these level sets over here by drawing these lines. And that's why it's a level set. As the level rises, I have different level sets. Now, this is a one-dimensional case. In two-dimensional case, generally speaking, what you have is a contour. So what is a contour? A contour is you have some kind of G is defined over X and Y. So we can think of a G as being a surface, right? And what would, like a hill, right? We have a hill, some shape. And we draw these planes that are parallel to the ground. And as we do that, what we get is we get these contours. So, you get the contours which are layered one on top of the other. And if you've seen a topographical map of a region, you understand exactly what's going on. These are the contours of some surface that are drawn over here, where the surface is something, and I'm kind of slowly raising up the level, and I get these continuous curves. Okay, now in general, it won't be continuous, but for these nice functions, we're going to get these continuous contours. Okay, so any questions about that? All right. So this is like if you're cooking, this is like slicing a potato. So each time you slice a potato, you can think of them as being level sets or contours. It's a nice way to explain it to somebody who's not mathematically oriented. So this is just slicing potatoes, or in this case, a kind of funny vegetable. At any rate, gxy equals c is nothing more than a specific contour, like so. Right? It's just got to be some contour like this, and that's gxy equals c. So no big deal. That's just a contour. So what the constraint tells us is that we are forced to walk along that contour. We cannot go above or below on this particular hill. We're going to have to stay on that level set. Imagine a road going around the edge of the hill, and you have to only go along that road. Okay. Now what we'll do is we'll start looking at f. Okay. In the same way as g is defined on the entire plane, I said it's continuous, twice differentiable on the entire plane. F is also continuous, twice differentiable on the entire plane. And just like G has its contours, F has its own contours. F's contours may be quite different. F contours may look like this. For example, just to kind of pick something. And what happens when I overlay this F contour on the G contour, right? What happens is that if I just consider this one over here, it's going to intersect F's contours. And maybe I should use a different color here. So let me use the green. And so I'm going to get these intersections with F contours over here. I'm just drawing parts of the contours, okay? But they just intersect these different contours of F, okay? So some contours of F are lower and some are higher, okay? For example, this is a lower contour, this is a higher contour. So as you walk along G, you're going to kind of intersect with the lower and higher contours. What's going to happen is that each contour corresponds to a specific value of F. Okay, so as you go along the G contour, the value of F is either going up or it's going down, right, compared to the previous value of F. So as you keep walking along, essentially what will happen is at each step you say, what's the value of F? Has it gone up or has it gone down? Has it gone up or gone down? You keep doing that, and what will happen is that at each step you're going to have an answer. Yes, it's gone up or it's gone down. Now, the point at which you want to stop is when you were first going up and now you're going down, right? You first go up and you go down, exactly like over here. So if you imagine now that we have decided already that G is the contour of G, and this is the set of values of F we find, okay? Exactly this over here. Well, what we want to do simply is to find those stationary points along F, where it's become a one-dimensional problem in some sense. I really have to find only those points of F where I'm going up and then I start going down. And this becomes those points where the constrained value of F is maximized. Okay? So if you look at those values, what will happen is that you're going to actually barely touch some kind of, and it's not going to intersect anymore, it's going to barely touch, like so, some extremal value of F. So if this were extremal value, it's just where you just touch that highest value of F, then everywhere else it's going to be lower. So that's your maximal value. So we're looking essentially, and this is where I'm getting, trying to motivate you, is those points where the contour of G and the contour of F are going to be tangential to each other. Okay? If you imagine overlaying this with this and we constrain ourselves, we want to find that point where the highest value of f is just tangential to this contour of g. And if you do that, what will happen is that the gradient of f and the gradient of g are going to match each other. Okay, not necessarily in sign. So what's a gradient? Probably should define that. So gradient is basically defined as this. Gradient of g is del of gx is just sort of partial del by del gxy is del by del x, del by del y, and you can think of it as a vector that's perpendicular to contour. Okay, this is just the partial derivative with respect to x and y. The partial derivative with respect to x tells you the slope with respect to x, and the partial derivative with respect to y tells you the slope with respect to y. If you take the vector of these two slopes, that's called the gradient, and basically you can think of it as a vector perpendicular to the contour. Now what we're saying over here is that tangential, by definition over here, just means that the two gradients are aligned. So we can say that del g and del f xy, okay, are the same. Well, it's not exactly the same. What we're going to basically say, we put a lambda over here. So lambda times del gxy is del fxy. So these two gradients are in the same direction, but they may be in opposite directions, and they may have different ratios because the slopes may be different. But at least we know for a fact that it's just a scalar multiplier. They're not pointing in different directions. Okay, so tangentiality just means that these two slope lines share the same gradient. It could be tangential sort of inwards, like so, in which case they'll have the same, or tangential outwards, in which case they'll have opposite signs. And the absolute value may also change, but we get this over here. Del fxy is lambda del gy. Okay, so let me pause for a minute. Does this make sense, right? So I'm trying to intuitively show you that as you walk along G's contours, we want to find the point where it's tangential to the highest f contour, and that tangential point, by definition, is where the two gradients match. And so mathematically represented as just saying that this gradient and this gradient are scalar multiple of each other, where lambda can be positive or negative. And so we have sort of a mathematical representation.
Is there always a tangential point?
Is there always a tangential point? Yeah. Again, when you have these things, when the functions are mathematically nice, right, then we are going to be tangential to some contour of f, because the contours are all infinitesimal anyway, right? It's not like we have integer constraints or anything like that. So infinitesimal contours. It's going to be tangential to some contour of f. And we want to find just that one point, because that is the point at which f is maximized subject to g. Yes?
Why actually, when the tangents are same, why is f is maximized?
Why is f maximized? Okay, let's go back to here. As we walk along the g contour, it's true, it has to be the case that f has some value there. Doesn't matter what it is. Let's say the value of x is d1, right? That's some value of d1, right? Now I step a little bit along the contour. Now the value of f is d2. Now what I'm saying here is that the contour, initial contour value for this was d1, and this was on the d2 contour. So I'm going up on the f hill from the d1 contour to d2 contour, or I'm going down on the d hill from d1 contour to d1 contour, d2 contour, right? If I draw this as d1 and I call this d2, for example, if that d1 intersects over here, and this d2 intersects over here, as I go from here to here, I'm actually dropping down on the f hill, right? So as I go up this contour level set, I'm going to go up and down the f hill, just like I'm going up and down over here. I want to find that contour of f such that, I'm not going up anymore. After that, it's all downhill. Okay, and that, of course, is going to be the maximum point of f subject to g. Now, the actual maximum point of f may be over here, right? But subject to g, the highest point may be over here. Maybe this is d3, and then what's going to happen is d3 is the one that is just barely touching over here. Any other questions over here? Okay. So that's why I said, you rode down the hill. As you go on this hill, that's a g hill, you keep evaluating the value of f, okay? And the point at which f attains its maximum is going to be the point with which on F's contour and G's contour you have the same gradient. Okay? So that is sort of the intuitive understanding, and to, I guess, to get this, you have to think about it a little bit more and probably remember your freshman calculus. I hope you studied a little bit of multivariate calculus, but if you remember that, or at least you just remember that the vectors are perpendicular to the contour, a little bit of thought should show you that in fact you're going to have the perpendicularity. So if we have this, now we can define what's called an auxiliary function. So now we're going to change from intuition to plug and chug. The plug and chug says we're going to define an auxiliary function f, and the f is defined to be nothing more than f x, y. So f is a function of x and y as well, plus lambda g x y minus c. Okay, that's the auxiliary function. And what we do is that we're going to look at the stationary points of fxy with respect to, I should actually, let me write this properly. This is not fxy, it's fxy lambda. Okay. Now, let me just kind of explain what's going on with this fxy over here. This auxiliary function, in sort of, again, to use the cookbook approach, says take the function you want to maximize, add to it lambda times the constraint like this. Okay? And if you do this, and actually you can do this for multiple constraints. There's no limit. You can have 10 constraints. You just say lambda 1 times this plus lambda 2 times this, etc. We can just keep adding them as we wish. Now, what we're going to do is we're going to find the maximum or the stationary points of f with respect to x, y, and lambda by setting the partial derivatives with respect to x, y, and lambda to 0. All right? Okay. Why are we doing this? Well, if you look at this carefully, you find that the partial derivative of this, okay, with respect to x and y are basically going to give you the points where the partial derivatives of where the gradient of fxy, okay, by setting it to 0, the gradient of fxy and the gradient of gxy minus c are going to basically be aligned with each other, because the partial derivative of c, of course, is 0. So when these two align with each other, what we're going to get is that we're going to get lambda del gxy equals del fxy, right? So in this function, just by setting the partial derivative of x and y to 0, we get the tangential points. And then when we set partial derivative of this with respect to lambda to 0, we get the constraint gxy equals c, and that comes out right away. So both the tangential points and both the tangential points over here as well as the constraint all drop out automatically by just setting the f xy lambda to 0. So just to kind of show that over here, let's just look at this. So basically partial x, or maybe I should just, if I define the gradient to be, just look at the gradient with respect to x, y, ignoring lambda, basically this is going to be gradient x, y, f minus lambda gradient x, y, g, okay? And we know that this is what you want to set to 0 because there's the tangential points. And so by just setting gradient f to 0, we get the tangential points. And then if you just take the partial del lambda f, this is basically nothing more than the g x y minus c. And if you set that to 0, so if you set this to 0, we are going to get, is it a plus or a minus? Okay, plus. It doesn't matter. Lambdas can be negative. So if you do this, we get the two gradients to align. And if we do this, we get the constraint. So this one single auxiliary function, f, x, y, lambda, allows us to get both the tangential points as well as the constraint in one shot. And that's why the auxiliary function is nice. And the nice thing is it generalizes as well. We can add to it lambda gxy, lambda 2, g2xy, lambda 3, etc. Keep adding that as you want. And when you set the partial with respect to lambda 1, lambda 2, lambda 3, lambda 4, each of those constraints will be automatically be given to you as well. So this Lagrangian multiplier approach kind of works. So this is called the Lagrangian multiplier. And then just, so it was invented by Lagrange, as you can imagine. Okay. So let me try and summarize the sort of the cookbook approach. We start with the function f. Now it has to be twice differentiable, continuous, and unbounded over the domain, so there are no edge points. Similarly, g is a nice function, and the constraint is gxy equals c. We define the auxiliary function over here, which is fxy plus lambda gxy minus c, and we set the partial derivatives with respect to x, y, and lambda to 0, and that gives us 3 equations. Okay, we solve the 3 equations simultaneously, and then that gives us the stationary points of capital F. Now, these stationary points can be maxima or minima. Constraint maxima, constraint minima. So we take the second derivative, and that tells us whether it's a maximum or minimum. So we have to do that over here. And the reason why you can do all this nicely is because f and g are both twice differentiable. So clearly, capital F is also twice differentiable, and that allows us to compute the constrained optima of this function over here. Okay. So any questions? And then I'll do an. Oh, it's already this late. Okay. So any questions? After we'll take a break, and then I'll do an example illustrating this in more detail. Any questions about this? Okay, so let me pause here, and all right. Is a unimodular matrix something with a determinant plus minus 1 or plus minus 1 and 0? Now, I was a bit confused because my reference was Papadimitriou and Stiglitz, and that book has been in print for, who knows, 18 years, I don't know, very long time, since 1990. And I was using the second edition, by which time I thought they'd found all their bugs. But in fact, Papadimitriou and Stiglitz is wrong. Okay, it says it defines unimodularity as determinant plus minus 1, but that's wrong. It actually is plus minus 1 and 0. So that's a correction I want to make. So I made the correction in the lecture notes, and I probably should write to Papadimitriou and tell him that there's a bug. Okay, so that's the first thing. And then the second question was about the weighted matching, where we had the situation I was saying basically that the sum of the sum over w, xuw, equals 1. And some of you came to me and said, oh, wait a minute, you can't do that because, what happens if you have this? You have just 3 nodes here. Well, this guy is not going to have anything, right? So it can't be the case that it's equal to 1. There was a mistake. It really should be less than equal to 1, right? Obviously, when you have more nodes here or more nodes there, some nodes are going to be unmatched. So that was a bug in the lecture notes as well. So I put up a new version of the lecture notes last night, I think, which has all of these bugs fixed. And somebody else, Francisco, sorry. Yes, thank you very much. So lots of corrections that you made, so put them all in as well. So it's all there. And so if you keep sending me corrections, I'll put it in. And so the version is as of yesterday, I think. It has at least all the corrections it received so far. The video for the second lecture is also online. And it looks like there's about a 3 to 4 day lag from the time I give the lecture to the time I get it. So I expect Tuesday's video to be available tomorrow, and then I'll put it up. So I'm putting it up as soon as I get it. So it seems to work. I know some of you are watching it. So Usman, I saw you watching it, so I know it works. All right, so I can stop with that now. Thank you. What I'm going to do now is to give you an example of Lagrangian optimization. Hopefully that will make things clearer what's going on. So again, I want to try and come up with an example which is realistic. So let's consider a company, and so there is some company over here, and it has its local intranet, and it has a link to an ISP, an internet service provider. And this is pretty normal. This is how every company connects to the world. They go to an ISP, and they say, okay, I want to get a link. Now, today, most links on the internet, in fact, as far as I know, all links on the internet are typically called all-you-can-eat. So they give you connectivity. They say your capacity is 45 megabits per second, and then we don't care how much data you send. It is what it is. Now, this is changing. Some of you have Rogers, and if you get Rogers, you know today that you have to pay a bandwidth cap. You get, I think, 60 gigabytes a month, and if you use more than 60 gigabytes a month, you have to pay more on a per megabyte basis. Also, for those of you who have cell phones and data transfer, you know Rogers, our friend, is going to charge you per byte. If you send SMS, you're paying the equivalent of $20,000 a megabyte, something like that. And both incoming and outgoing for Telus and Bell, but not Rogers. And so you have this notion of paying by the byte. So we're going to have over here, this link is in the future, so they're going to pay by the byte. And this is coming, I'm sure. And so the cost, we're going to say that the cost of a link, oh, wait a minute. Actually, for this one, you don't need to pay by the byte, but whatever. Cost of a link is going to be KB. Okay, and for our purposes, we'll just say if you send B bytes, you're going to pay KB cost. Now you can also view this as saying if the capacity of this link is B, then you're going to pay KB. It doesn't really matter. Mathematically, it kind of boils down to the same thing. So we'll just say cost is KB. And also, let's say the mean delay on the link, we'll call that D. Again, you can think of this D as being the time taken for transferring B bytes or the delay on this link overall. Again, it doesn't really matter. The thing that matters is that we often have this kind of relationship, which is BD equals 1. If you increase increase the link capacity, then the delay goes down. Okay? So I guess I can't. All right, let me take this away. We're not paying by the byte. Sorry. Because if you pay by the byte, when you send more, the delay will go up as well. So ignore that. All right, we're going to restart from again. Rewind to whatever it was. All right. I'm going to do this. I thought I could do it both at the same time, but I was too clever for my own good. So I'm going to do it just one thing at a time. Let's do it simply. So you go to the provider and say, I want to buy a link of capacity B. The provider says, okay, if you buy a link of capacity B, I'm going to charge you KB. All right, fine. And the mean delay on that link is D. And the faster the link you buy, the less delay you have. Okay, so that works out. The other way around, it's a bit messier. I can make it work, but not in real time. All right, so let's just do this. So this is a constraint. This constraint is sort of the laws of physics in some sense. Okay, the higher the capacity. So you can imagine, this kind of works out. If you have a gigabit link, you're basically going to see less delay than if you have a 300 bit per second link. Okay, mean delays are going to be higher for obvious reasons. So, all right, so we have this, and now we want to know what is the benefit to the user? What is the benefit to the company? Well, let's call the benefit, we'll denote that by U. All right, and that stands for utility. Again, when we do decision theory and game theory, we'll use U all the time, so I just want to bring it up over here. And what we're going to do is to say that the benefit U goes down with delay. So as delay increases, utility decreases, right? And of course, as the cost increases, utility decreases again. All right? And just to make things simple, we'll assume that the relationships are linear. Okay? Now, again, we don't have to be linear, but it turns out to be easy to do an example when it's linear. But you can think of, and in fact, all of our stuff will work, even if it's quadratic or anything else. Anything polynomial will work fine. But we're just going to keep it linear just to make things simple. So we'll define U to be minus KB minus D. Okay? That's very simple. As the cost goes up, my utility goes down. As my delay goes up, utility goes down. Okay? You can see it's linear. Okay? And so, in fact, I could have used this. I could have used linear programming to solve it, but I'm going to use Lagrangian techniques just to illustrate it. Okay? So we have U equals KB minus D, and this is of the form Fxy. Right? It's basically U of BD. Right? Utility of any value BD. So you can think of the plane has two axes, the B axis and the D axis. And as we move along the BD plane, we get different values of U. Of course, everything is going to be negative. Okay? U, in fact, is never going to be positive, but that's fine. And we want to, of course, maximize u. We want to find the least negative point. And here the constraint, BD equals 1. This is basically of the form G, X, Y, okay, equals C. That's obvious. In this case, it's just G is just the multiplication operator. BD equals 1. All right? So we have the problem now set up. So I just want to, again, illustrate to you the thought process. So what you do is the company says, I want to be the happiest possible. You say, okay, what is your provider charging you? Okay, it's charging you something, and we make it some function of B. In this case, we make it linear, but it doesn't have to be linear. It just has to be something twice differentiable. All right? And then you say, okay, how is your link delay related to your bandwidth? And we have, again, we said 1 over here. It could be any constant, right? And we sort of say, okay, this is BD is equal to some constant. We'll just use it 1 just to be consistent. And all we're saying over here is that B and D are inversely proportional to each other. Again, we could choose any function that we want, twice differentiable. So that's how you kind of go in with your consultant hat into a company, right? And then you say, all right, I've got this. Then you say, okay, your utility function must look like this. It should be like something that decreases as you increase the cost, and something that decreases as you increase the delay. And so we set up this thing. Again, it doesn't have to be linear. It can be anything else. All right, so I'm just showing you that, when we talked about this, it looked pretty, abstract. But it actually boils down to something pretty straightforward over here. And now we can define F. F is equal to minus KB minus D plus lambda times BD minus 1. Right? That's just exactly the way I said earlier. This is F, and that's G, and we have the Lagrange multiplier. All we need to do is to set the partial derivatives with respect to x, y, and lambda to 0. So how do we do that? If we set the partial derivative with respect to x to 0, in this case, B, D to 0. So the first one, del by del B equals just nothing more than K minus K plus lambda D equals 0. And then del by del D, this implies minus 1 plus lambda B equals 0. And then del by del lambda implies BD equals 1. That's just the constraint. It just pops right out. And we want to find the point at which all three equations are true. So we have three equations in three variables, lambda, B, and D. And we can solve it to get the solution, which is that B equals 1 over under root K, and D equals under root K, obviously because BD equals 1. And the value of U at this point, so B star, I guess it should be D star is this. And the value of U at B star and D star equals minus 2 under root K. All right? And we only have one stationary point. Okay. Now we could do the second derivative, etc., and kind of find this. But by inspection, it's obviously it's clear that this is going to be the maximum value for U. Why is it the maximum value for U? Because I can make U as small as I want. Okay. Simply by making, in this case, B as large as I want. To make B very large or D very large, my U is going to go as small as I want to make it. So obviously, this has to be the highest point and not the lowest point. It's single-peaked, and in fact, it's linear, so it's even simpler than that. At any rate, we find that the maximum possible utility is minus 2 root K, and we also know the bandwidth to acquire and what delay you're going to get. So the answer is you go to the ISP and you say, I want to purchase a link with capacity 1 over root K, right? And what is K? K is the price that was given by the provider. So the K says, if the ISP says your cost for for 1 megabit per link is $100, and your price for 2 megabit link is $200, etc. With the appropriate units, we can find out what K is. Okay, and we just put it over here. I mean, this is what we get. This is the link that we want to get. Okay, so we have an optimal solution using from Lagrangian optimization. Okay, so any questions about this so far? So one of the things you may want to try, again, I probably should put it in the homework, maybe I did, anyway, is what happens when you don't have these simple linear functions, you have quadratics and so on. Well, what happens? You still do the same thing. These things look a bit more complex. And instead of getting simultaneous linear equations, you get simultaneous quadratics and so on. But you still have 3 equations and 3 variables, and you should be able to solve it. Okay, I mean, if necessary, you can resort to a numerical solution. Stick it in Maple and see what it says. But basically, this is the approach, and this is Lagrangian optimization. Okay, any questions on this so far? Okay, good. This is a very powerful tool, and as I said, with game theory, you kind of end up with this all the time, and so it's a nice thing to know. Okay, so far we've looked at a situation where you want to maximize f subject to g equals c. Okay, what happens if we had this? We had g greater than equal to c. Okay, and it turns out that this becomes quite a bit harder. Okay, we don't have these contours level sets anymore. We can't walk along these level sets and find where f is tangential. We can't do that anymore. So we have, in fact, an infinity of level sets where g is valid, because you're just saying g has to be above this, right? So you can immediately see by going from a equal to a greater than or less than, suddenly the whole problem changes its character. Okay, and for a long time people didn't know exactly how to solve it. Certainly Lagrangian techniques don't work. And there was a master's thesis by a guy called Karush in the 1940s, I can't remember exactly when. And then 2 other people, Kuhn and Tucker, improved this work and made it simpler, and came up with what are called the Kkt conditions for Karush, Kuhn, Tucker. And these Karush, Kuhn, Tucker conditions allow us to maximize a function f over some vector x subject to, and let me be sure I get the right values over here, m equality conditions, and these are of the form g I x equals c or 0, doesn't really matter, and there's 1 less than equal to I, 0 less than equal to I less than equal to m, and L inequality conditions. And these are represented as hj less than equal to 0, x, and 0 less than equal to j less than equal to L. Okay, so this is the statement of the problem. So you have f, you want to maximize subject to m equality and L inequality conditions, and so it's a little bit more general. The question is, can you do it? And the answer is yes if f is nice, g is nice, and h is nice. And what we mean by this is that f has to be something called convex. I'll explain what that is. All the g's have to be convex, and the h have to be linear. If h is also convex, you're out of luck. So you can only do it with respect to linear. And you can sort of see with inequality, if you have something that's messy, you don't know what's going to happen above that level set. Whereas if it's linear, above the level set, its behavior is more or less predictable. Okay, it makes life easier. So for inequality, we require these to be linear. But these equalities can be arbitrary, which is, of course, same as Lagrangian. Lagrangian doesn't require these to be anything specific, just twice differentiable. But here we require them to be convex, and this has to be convex. So what does convex mean? A convex curve, mathematically, is a curve like this, where I can take any 2 points and I draw a chord between them. The function always lies below the chord. Okay, that's what convexity means. Okay, so let's take an example of something that's not convex. If you take something like this, well, over here it goes above, okay, and here it always stays below. So what convexity really means is that it's like a single bowl, okay. It's just a bowl, Okay, you can't really, a curve like this, that's not convex because I can find this chord over here and it goes below, right? And now you have to generalize this to multiple dimensions, but all we really say is that if you have any point x and any point y, then we can define essentially any intermediate point is given by x plus vector x plus alpha x plus 1 minus alpha y. Right? This is just interpolation. As alpha goes from between 0 and 1, the vector sum of these two vectors is going to give you all intermediate points on the line from x to y. That's just simple vector analysis. And so we're just going to say that for all alpha, okay, f of this, okay, is less than equal to the actual value alpha x plus 1 minus alpha y. So this is the mathematical statement of convexity. This basically says that the function value at this point is less than the value at this point. So if I draw a line from here to here, the value at this point is this, the function value is this, and it's always going to be below. That's convexity. And intuitively it means I don't have kind of wavy stuff. I have something that's nice. Okay. Now, it turns out that many real things are not convex. Okay. So most real functions are not convex. So this, for example, is one of the things I told you about earlier, is the saturation effect of utility. As we increase the amount of goods, as I increase the goods, as they call it in economics, and this is the utility, you get a saturation effect. As you increase the goods, in the beginning, you don't get much effect at all. Then after a while, you get a lot of benefit. And then after this point, it saturates. You're not going to get any more benefit at all. So if you draw a line like this, you will find it's not convex. Okay. However, in almost all of economic theory and all of game theory, implicitly, they call it a technical condition, and they stick it in a footnote saying, we assume that all the g's are convex. And if G is a utility function of this sort, well, it's not convex. And so the quote-unquote technical condition allows you to solve using the Kkt conditions any kind, many kinds of games. So there's one of these kind of big problems with game theory, and I'll tell you about some other big problems with game theory later. But this is one of these big problems. So whenever you go to an economics or game theory talk, the first thing you ask, how do you know it's convex? Do you have any saturation? Oh, yes, you do. Then how do you know it's convex? Well, it's not convex. Then they'll say, well, I can't solve it then. Sorry. So they can solve it in a universe which is not real. So anyway, so this is a condition you got to watch out for. Okay, you got to watch out for the single peakedness. But all the Kkt conditions assume convexity, and in particular, Kkt is used to prove one of these fundamental theorems in economics called the Peirce-Arrow theorem, which I won't get into right now, but I will later. All right. So what are the conditions? I'm not going to tell you. This is painful to write out. It's all in the lecture notes. It has to do essentially with saying that we're going to find a stationary point with some extra multipliers. Instead of just having lambdas, I'm going to have lambdas and mu's. And I'm going to basically find these points where everything lines up just right. And it's in the notes. Again, the approach I'm taking here is, okay, plug and chug, right? So you get a system. You say, all right, it's got inequality constraints. What do I do? What do you do? Well, you first check whether the linear inequality constraints. If you are, and the other constraints are convex, and you can prove convexity, at least in the range of, in the domain of interest, then you can use the Kkt conditions and say, okay, this is a solution, and everything is happy. If it's not satisfying this, then you're forced to go to heuristic conditions. But let's say it is. What you do is you pull out your book, you look at the Kkt conditions, and you prove essentially that each of the conditions actually holds. And when each of these holds, you can just kind of find the optimal point using these Kkt conditions, and you're done. Okay, and so again, when you read a paper, what you'll find is you'll say, okay, this is a solution, this is a problem that we pose, and we are going to assume convexity of these things, we're going to assume linearity of these things, and we apply the conditions, and here's the solution, and that's the way you do it. So again, this is sort of how you can both read and figure out what's wrong with the paper. You can say, well, it's not convex. Oh, well, sorry. Okay. Okay. Any questions about this so far? Yes.
If we have a function, can be divided like in
Yeah, but see, if you do that, then you have to look at the boundary conditions, because remember what I said, Fermat's theorem says that the maximum or the minimum occurs either at the inflection points or at the boundary, okay, or at the points of non-differentiability, right, where you have discontinuous jumps or non-differentiable points. If you have a function that goes like this, then of course there's a non-differentiable point over here. So if you introduce these discontinuities, then you have to check for each of those limit points and the non-discontinuous points whether those are the maxima. So the short answer is yes, but then you have to be careful. You can't just do it. You have to introduce all these points and check for them. So you have to find essentially the region of convexity, and then you have to find along that entire region at the limit points where the maxima arises at the limit points, right? Because it's a limit point. So yes, that can be done. That can be done. The other approach, of course, is to kind of do a linear approximation, right? You say, okay, I only care about this linear approximation, and then the limit points are very easy to find because it's linear, right? You can just find the endpoints and plug it in and see whether it's maximum over there or not. Yeah. Any other questions? Yes?
Why could we use the surplus variable like we did in the linear one? Is it because the two will have different number of variables and the differentiation and partial differentiation wouldn't be possible or something else?
So why don't we use surplus? So when you introduce a surplus variable, you're essentially changing the dimensionality of the problem, right? You're adding extra dimension. Now, if I say over here that hx s equals 0, right? Where is that s coming into G?
Yeah.
Right? I can't have an equality over here anymore. So, I can't increase the dimensionality like I did in a linear program, because in a linear program, increase the dimensionality, I can just kind of over here, yeah, I don't know. The short answer is I'm just guessing over here why they don't do it. You could put an extra variable over here, make this equality, and then stick it over here, perhaps. I don't know, but at first glance, it doesn't seem like it would work because the dimensionality is changing, and the G is not defined in that dimensionality, right? G is a function of, let's say, 10 variables, a 10-dimensional quantity. If you introduce, 4 more dimensions, then what is G in those dimensions? Is it 0? Is it undefined? What happens? It doesn't make. Is it convex? Is it differentiable? Right? We don't know. So that's a problem over here. Any other questions? Okay, so let me pause here, and after this we'll talk about something a bit less mathematically hairy, which is heuristic optimization. In many cases, we actually don't have twice differentiable nice functions. We just have some function, and we know its value at a particular point, but that's all we know. We kind of have the function f defined at some point in some n-dimensional space, and we want to optimize it, but we have no clue about the mathematical form of f. So let me give an example of this. So let's say I have a wireless access point over here. And this is some work that I did with Nabil, who's sitting in the back. So I have a wireless access point, and let's call this 1, and I have another access point, AP2. And I have some laptop over here, and then I have another laptop over here. All right? And laptop 1 is using AP1, laptop 2 is using AP2. Okay, so far so good. Now, it turns out that I have a particular power level on this link, so I'll call that, power of AP1 equals P1, and the power of AP2 equals P2. Now, that tells me what is the power, how much energy I'm sticking into the air. As you can imagine, if I increase the power, this one does better. Okay, if I do the power, it goes better, it goes faster. Great. So if I have very low power, I'm going to get a rate of, say, 6 megabits per second. I increase the power, it goes up to 36, 48, and goes up to 54 megabits per second, and life is great. Okay, so in some sense, I can say utility, which I'll define as U, increases as P1 increases, because it's going well. And similarly for U2, if utility increases as P2 increases, because the same thing happens over here. But I have a problem. Okay, what's the problem? Problem is that if I have too much power over here, that is going to start interfering with this one over here. And similarly, if I have too much power over here, that's going to interfere with this one over here. So I get the situation where if utility decreases as P1 increases, and utility decreases as P2 increases. So what I have is that, sorry? Yeah, you get both. You get utility both increasing and decreasing as P1 and P2 increase. So if I define utility as some function of P1, P2, I have a situation where I really don't know whether it's going to be increasing or decreasing. Okay, maybe it's going to increase, maybe it's going to decrease. And these functions are not nice, okay, because to begin with, these are not differentiable. They're not continuous because the power levels are not real quantities. They're integers, okay. So I have an integer linear programming type problem. I have integer values. Moreover, the utility as I increase the power is also time varying, okay. So I can increase the power and somebody walks down the hallway, all right, or somebody opens a door and then the wireless conditions change, and in fact, because the wireless conditions change, even though I increase the power, utility may go down, all right. So it's time varying. So what I have really is something like this. I can measure the utility as the total amount of throughput that can be delivered to the laptops from the access point. So this guy is trying to download a video, this guy is trying to download a video and watch it, all right. So I can say, okay, how many bits per second did you get on this link? How many bits per second did you get on that link? I can measure both of them. That gives me the utility for that value P1, P2. What I'm trying to motivate over here is that if I increase P1 or decrease P1 or increase P2 or decrease P2, I don't really know what's going to happen to utility. Maybe it'll go up, maybe it'll go down, maybe the environment changes, and even though I didn't change these guys, it really changed on me. Okay. So what I'm going to assume for now is that environment doesn't change. Let's just assume that things are happening so fast that environment doesn't change. Okay, and it turns out to be something we can assume. Then what I can do is this. For some power level P1, I can define a neighbor of P1 as being, P1 plus and another neighbor P1 minus. It says increase power one step up or decrease power one step down. Similarly, this one, P2, can go to P2 plus and can go to P2 down. These are not in the lecture notes, by the way, so I'm just making this up as I go along. But actually, I know this already, so I don't need to make it up. At any rate, what we can now define is neighbors of U like this. You can say U, P1, P2, okay? That's the base, and then it has a, okay, so I can say P1 plus, and then I can go to U, P1 minus, P2, etc. I have two more neighbors. I have four neighbors, okay? It basically says increase P1 by a little, decrease P1 by little, increase P2 by little, decrease P2 by little. I have four possible neighbors. Of course, one says don't do anything. That's another one over here. That's the original point. What am I defining? I'm defining over here neighbors of a point. Okay, what is this point? The point is P1, P2. It's the power levels. Okay, what I'm doing gradually is to show you the modeling of the system. Okay, the system I started out with was saying I have access points in laptops. All right, fine. Now I'm going from there to saying, what is my control variable? The control variable is the power. Then I'm showing you that we actually have two control variables, P1 and P2, and I'm explaining to you how the benefit, in this case fxy, in this case uxy, or up1, P2, is going to change. And the problem is we don't have nice mathematical relationship for u. So what am I going to do is I'm going to have some value here, and I have some neighbors, and I can evaluate the utility at those neighbors. How? I change the power, I see whether throughput goes up or goes down. I add it to, I figure out what the utility is. So I know the utility at those points by actually carrying out the experiment. But I don't know the shape of the space, and none of these nice Kkt conditions or anything like that holds. What do I do? Right? What you do over here is what's called hill climbing. How does it work? He says, okay, I'm at this point. I know where I am right now. At least I'm standing on firm ground. I look at my neighbors. And what I'll do is I'll evaluate whether the neighbor is above or below me. If the neighbor is above, I go there, right? And then I repeat the process. I find all those neighbors. If it's above, I go there. And I keep doing this. And eventually, I hope to find the top of the hill. So this is like you're put on a hillside in the dark with your blindfolded, and you're dropped off on a hill, and somebody says, climb the hill. All right. So what you do is you put your 1 foot like this, 1 foot like this on each side. So, oh yeah, that's the upward direction, and you go there and you repeat this process. Even though it's totally dark, you don't know what the hill looks like. You're going to find the top if two conditions hold. First, you're able to find your neighbors. It means you can actually probe your neighbors around you. And second, the hill has to be convex. The hill has to have a single peak. All right, it has to look like this. Because you start over here and you kind of work your way up, etc., you eventually get to the top. You may actually go in a spiral like this. You go around and then that's okay. You'll get to the top anyway. But what happens if you have a hill like this? Well, you'll start over here. You'll keep climbing to the top. At this point, you say, oh, I'm at the top. So that's a problem. Okay? So whenever you have this kind of approach, we need to do something else. But for now, I just want to focus on this one thing, which is called hill climbing with single peak. All right? And that's the basic hill climbing technique. All right? And as you can see, it should work over here. I start over here, increase the power. If it gets better, fine, I try it once more. I find all the neighbors, and I keep doing it. At some point, essentially all the neighbors are going to have worse power. And then I say, okay, this is the best possible configuration. I'm done. And that's your optimization. Okay? It's a practical, very, very practical approach. In fact, very widely used. Okay, so let's put a little bit more thought into it. And what we do here is that let's say that I'm going to look at a bunch of neighbors. So let me go back to a little bit of a... So I have some kind of plane, let's say, has some hill defined on this. I take some point over here, evaluate the value of the function on that plane. Let's say I choose 4 neighbors, and I find the values there. Well, the dumbest way of doing things is to say, if I find any neighbor that has a higher value, go there. So if this is higher, go here. That's it. But I can be a bit smarter. I can actually look at all the neighbors. And then what I'll do is I'll find the one which gives me the greatest benefit, the highest gain, what's called the steepest gradient. And I'll go to the one that's the steepest gradient. And that's basically called steepest gradient hill climbing. And it's kind of an obvious thing to do. Okay, so that's one variation. The other variation is like this. I'm over here. I go to this neighbor, and okay, I tried these guys, and these didn't work out. I went over here. Now this guy says go here, okay, and he tried this, didn't work. These guys were not good. Went over here. So that's 0.1. This is 0.2. Okay, goes to 0.3, and then let's say we end up over here at 0.4, and this is a neighbor of 4. We already know that this is worse than 1, 1 is worse than 2, 2 is worse than 3, 3 is worse than 4. So transitivity, we don't even need to evaluate this anymore. There's no point in doing it, right? So what we do is we maintain what's called a taboo list. And taboo list is just a list of all the places that are no good. Right? These are all the points that it's no good because you've already been there before, and so there's no point in evaluating it. So what happens is when 4 creates its neighbors, it checks whether anything is in the taboo list. If it is, it drops it, and this is what's called taboo search. Again, it's pretty straightforward. You always should do taboo search because memory costs you nothing these days. All right, so let's do any questions about this so far? Yes?
So if we are using hill climbing, it means that the function is not nice, so we cannot check the convexity.
That's right.
So if we cannot check the convexity, how can we assure that the...
We cannot. We cannot. If you don't do anything, you'll be stuck at some bad point. It's better than doing nothing.
But so we cannot find the optimal value.
No.
We can only find the local optimal.
That's correct. I'm coming to that. Okay. Yes, without taking some other measures, which we'll come to in just a minute, you will almost surely end up at the local maximum or local minimum. Right? Okay. But yeah, we'll come to that. Okay, I just want to talk about one more thing, and then we'll talk about non-convex situations. The other thing, but in these two things should be clear, right? The steepest gradient and taboo search. So let me tell you about the third thing, which is like this. I want to maximize the function u over here. I want to maximize, but I want to subject it to something else. Subject to g, some function g. All right. For example, Over here, I might say that the sum of the two powers, P1 plus P2, must equal something, right? P1 plus P2 equals, I don't know, some value A, okay? Because I don't want to spend too much energy, so I want to do something, I don't know, right? How can we incorporate this? It turns out to be very easy to do, because what we do is this. We take the neighbor and we create all these candidate, we take this point, we look at all the candidate neighbors, like so. Then we evaluate G on all the candidate values. If any of them is not satisfying G, we drop it out. So these two guys didn't satisfy G, we drop it out. For in our case, for example, what this means is if you have P1, P2, maybe you can go from here only to P1 plus P2 minus, or P1 minus P2 plus, because only they satisfy the sum constraint over here, P1 plus P2 equals A, okay, for example, all right? So as you can see, I can eliminate those 2 points, which is P1 plus P2 plus and P1 minus P2 minus. So when you're doing hill climbing like this, you can at least make it very easy to do constrained hill climbing. And this is actually a non-intuitive observation. You can actually do this even in other cases. For example, when you're doing other kinds of hill climbing, if you want to introduce constraints, it turns out to be very simple to introduce the constraints as part of the search. So you do a constraint search, and then you constraint search, and by construction, you're guaranteed that the hill top is going to also be constrained by definition. Okay? Any questions on this so far? Okay, so let's go into the non-convex thing. So non-convex case or non-single convex case, we may have a hill that looks like this. Okay? And so maybe you start here, you end up over here. If you start anywhere in this region, you'll end up there. If you start in this region, you'll end up there. And if you start in this region, you end up there. And you start in this region, you end up there. So in fact, what we're finding is essentially the stationary points, and we're finding the domains in which these stationary points happen to be the maxima, right? Pretty straightforward. So if I start and choose only one initial value, I'm going to end up here, 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 or here. But I'm going to be clever. I can say, okay, you know what? I'm going to choose 2,000 initial values. Okay? Why not? Just try 2,000 initial values randomly all across the space. Chances are pretty good that some of them will end up here. And then you say, okay, all the rest was wasted time, but I got the maximum value over here. So this is what's called shotgun hill climbing. Again, it's a very, because you just take a shotgun, you spray initial values all over the place. And this turns out to be very, very useful in practice. You just choose a bunch of initial values, and if you choose enough, so one technique you can do is like this. You take initial value over here, and you find it goes there. Great. You choose another initial value, it goes there. You choose another initial value, it goes here. You choose another initial value, it goes there. Another initial value, it goes there, etc. And you know what? You find that what's going to happen is, if you look at time on this axis and the maxima that you find on this axis, you're going to find this kind of situation. At some point, you're not finding any more maxima. Okay, you're probing the entire space, but you're not finding any more maxima. So at some point over here, you say, you know what? I think I found the global maximum. Okay, because it's not getting any better. Or you may have a performance criterion that says, I want to be within Y% of optimal, where optimal is defined in some fashion. Maybe by using some approximations, you can compute the approximate maximum. Or by using, in case of most computer science problems, if you do offline algorithm, offline is always optimal. You can actually look at the future, you can figure out what the future is. So if the offline optimal turns out to have some value, let's say 100, you say, look, if I get to 80, it's good enough. If I get to 80 on most problem sizes, it's good enough because I'm willing to go 20% as slop. If I find I get to 80 at some point, I say, great, I'm done. So there is some, as long as the initial points are chosen randomly enough, so be careful about randomizing that, you will, in fact, find the global maximum, and so you can use this approach to essentially compute the global maximum. Yes?
How do we know that there exists?
You don't.
So
you don't.
No,
there is, no, are you saying, are you sure? The global maximum exists by definition, right? Some value's got to be higher than all the others.
No, it might be a monotonically increasing function.
Oh, okay.
somewhere.
Oh, no. If it's monotonically on an infinite domain, of course, you're out of luck. But typically, in all practical problems, the domain is restricted, right? We don't have infinite anything. So we always have limited domain. And yeah, so again, we'll just immediately try to test the boundary points. Just, it's obvious you should do the boundary points. Then you do this, right? So, yeah. Any other questions over this? Okay. So this is shotgun hill climbing. And again, it's something you really should remember because this works out very, very well in practice. You can combine shotgun with taboo and combine it with steepest gradient and so on. I want to give you one more approach for the same kind of thing. It's called simulated annealing. And this was a really hot topic about 20 years ago, but by now people have given up doing research, but it's widely used in practice. So what is annealing? Okay, what is annealing? So in Japan and in Damascus, the sword makers figured out a way to make very, very strong swords. And what they would do is they would take a piece of metal, steel, and they would heat it, and then they'd put it in cold water, and then they'd beat it. And then they'd take it out, heat it, put it in cold water, and beat it again. And they would do this over and over again, thousands of times. And at the end of it, what was happening was that the steel would acquire these properties that made it very, very strong. So these Japanese katana swords are very, very strong. And in fact, the Damascus swords are equally famous for their approach. So that's called annealing. So what's going on here is, I'm sorry?
They do something else.
They do something else too. Okay.
Like it's like a piece of metal like this.
Yeah.
Then they put it in the fire. Then they kind of cut it in half. They put two pieces together.
Oh, and then, yeah, okay, yeah. So they fold it over,
Yeah.
and then they hammer it together, yeah. So they basically, it makes the crystal structures very strong, and, get new crystal structures coming out of it. That's called annealing. Simulated annealing is similar. What we do over here is that we are going to essentially climb a hill, okay? So the hill looks like this. And just like the sword maker raises the temperature and kind of lowers it and raises and lowers it, what we're going to do over here is we are going to have this temperature value that actually is monotone. The temperature decreases with time. Okay, temperature tends to 0. But what we're going to do is that when the temperature is high, we allow large movements inside the optimal space, in the optimization space. And when the temperature goes low, we allow only small movements. What does that mean? Okay, what it means is like this. I have a point over here, and I'm going to look at its neighboring points. So okay, actually I shouldn't look at this point. Let me look at this point over here. And this point, as you can see, is going to end up with this as its local optimum, but I want to avoid that. Okay. So what I do is this. If the temperature is high, I will allow it to go up or allow it to go down. Okay. As long as the movement up or down is bounded by some function of t. So I have something called the acceptance function a of t, and the acceptance function a of t is defined by basically saying that I will accept it as a valid neighbor even if it goes down. Okay, even if the value of the utility or value of the function goes down as a function of t. Okay, so what's going on here? We start at some point and we set the temperature to be high. Okay, and we generate the neighbors. This is a valid neighbor. It's higher. This neighbor is lower, but we'll still accept it. So there are two possible neighbors, and we find the steepest gradient or whatever. Let's say we pick this one. We're lucky, and let's say we get to the local maximum. That's where actually things get interesting. When the local maximum, you reach a local maximum and the temperature is high, what happens is you're allowed to escape the maximum by going down and going up like this and then climbing this hill over here. So if you have a lot of energy, okay, you can escape local maximum by jumping into different hill or by going down and then going up again, okay, because these become acceptable or valid neighbors. However, as time increases and temperature decreases, you will start accepting fewer and fewer decreases as valid. You'll only start accepting increases. And the idea is that in the beginning, you can start somewhere in the space. So you have some single peak thing over here. In the beginning, you might start somewhere in this random point over here, okay, and you may end up over here. So you need to be allowed to kind of go down or kind of find this slope somehow. But as the temperature decreases, you should only be going up, okay? So I'm just giving you sort of a rough idea. Another variant of this says, in the beginning, choose very far neighbors. And as temperature decreases, choose only nearby neighbors. Again, you have a similar effect. In the beginning, you can make big jumps, okay, out of these local hills. But as temperature decreases, you only make small jumps, and hopefully you'll find the global optimum. So it's completely heuristic, but it has been found that for many kinds of problems, this kind of approach where we accept decreases earlier in the optimization and then we can only go up later on turns out to be something that works out well in practice. Okay, so I'm going to just leave it at that. All of the kind of the whole problem becomes how to define the acceptance function properly as a function of temperature. And if you mess this up, what will happen is you'll get, and if starts rejecting things too soon, you'll end up at a local maximum. But if you accept things too slow, you will jump away from the global into a local somewhere. And so you have to carefully balance this. And there's an enormous literature on how to do this, how to choose these acceptance functions so that these things don't happen. And I'm just going to mention it to you. So again, if you say, I'm going to do hill climbing, you may want to consider using simulated annealing. Okay. Any questions about this so far? No. How this relates to making soaps, I don't exactly know. Okay, other than the fact that temperature eventually goes down. But this is what's going on over here. Any questions? Okay, I'm going to. There's some more detail and a little bit more formalization in the lecture notes. I'm not going to talk about it. I'm just going to focus on one last thing before we break. So we're going to end. So your interest level should come back up on that curve. Okay, and this is called genetic algorithms. And I put it in because it's kind of fun. It's really I've seen it being used only in a couple of different places. Mostly for optimizing RF circuits, in some cases for optimizing scheduling. But anyway, let me explain to you how it works. So the basis for genetic algorithm is sort of to mimic the law of evolution, to mimic sort of Darwinian evolution. And the idea is like this. I have some vector x, and I represent that as x1, xn. This is the normal multidimensional vector. And in fact, we're going to look at very large dimensionalities. Let's say 2,000 dimensional space. We have 2,000 elements in this vector. The intuition in the genetic algorithm is like this. It says that some of these values of the x's actually are more important than other values of x's. In other words, it could be the case that fx is going to be affected by this one and not very much by the others. Okay, so it's really pretty much independent of the values of, let's say, x1500, but x1499. Boy, that really makes a difference. X1499 is set to 20. Everything is great, but if it's something else, it's going to be bad. But you don't know this. Nobody knows this, again, because you're sort of operating in the dark. So what you do is this. You take a bunch of strings, which is like DNA, right, which correspond to the x's. So we have x1 vector, x2 vector, and let's say we have, a million such strings, so x million. And these are just like the shotgun approach, just random values, okay, just completely random values. Then what we do is, for all the million values, we evaluate f on each of them. Okay? What are we getting? We're getting sort of in this million dimensional, in this n-dimensional space, we're getting a million different values, and some of them are greater than others, right? So what we do is we pick some subset of them, okay? We pick some subset of them, let's say the top 10%, and so this is the initial set of vectors. We evaluate f and we rank them, and this is the top 10%. And we say these top 10% are the winners of this round, and we essentially ignore all these guys over here. And now these top 10% has some features in them which make them good. We don't know what they are, right? It's the value of x1499 is 20, but we don't know what it is. But guess what? All the values over here, which are high, must have shared the feature x1499 is 20, right? Which is good. So what we're going to do is we have some concentration of things over here. We're going to now, in the next round, expand this again to another million. But what we're going to do is we're going to do over here mutations. and what is it called? Crossing? What is it? Crossover. Thank you. Mutations and crossover. With mutation, what we do is, let's say there's some value over here, there's some 2000 element thing. I'm just going to randomly flip some values. If they're 0, 1 vectors, I can flip zeros to ones. If they're integers or reals, I can just perturb it in some fashion, and that gives me some set of things. These are just mutants. And of course, there is the null mutant which says, don't do anything. And then we can have crossover. We take some parts of this string, some of this, some of this, some of this, some of this, combine them together and make one string over here, which is kind of crossed over. And we can use different kinds of rules. We can say we'll cross over only the top 10, we'll cross the top with the bottom, whatever. There are all sorts of rules for doing this. And we generate, in this fashion, 1 million more. We do the same thing all over again. We find the value of f on all of them, find the top guys, drop the bottom, and take the top 10% or 5% or whatever, and create mutants and crossovers, and keep doing this, Basically throw a supercomputer at it to keep doing this. At the end of it, what we hope to find is a value of f that is the best. Okay? If you think about it in the hill climbing approach, what's going on is that we have some kind of multidimensional hill like this, and we're choosing a lot of initial points all over the place. Okay? A lot of initial starting points all over the place. Then we find the top set over here. These are the guys which are, we're not doing any hill climbing, we're just finding the top values over here. And then we are trying to find mutants. What are mutants? Neighbors, right? In that space. Mutants and that's neighbors. We're finding the neighbors of the top guys. And then we're also finding these new values which you never suspected existed. So we have some hill like this, a big hill in the middle, and some hill like this. We take this guy, and we cross them over, we find this guy, right? We hope we find this guy. Again, we're in this enormous space. But people find that for certain classes of problems, if you express it in this way, and the dimensionality is very large, in fact, at the end of the system, at the end of it, we actually find very nice solutions, which look really good. So in the RF circuit space, I'll give you an example of this that I remember from some years ago. They were trying to design these RF circuits, analog circuits for, I don't know what, some antennas or cell phones. I don't know exactly what it was. And so they expressed each possible value of that design in terms of these variables. And there are lots and lots of variables, as you can imagine. Okay? And so, for example, one way of doing a circuit design might be that I have a set of points, and I can have a line from here to here, or a line from here to here, line from here to here, and so on, right? And I can just define this. So if the antenna shape is supposed to be like this, some bizarre shape, you would never think of coming up with this, but this really works very well. All right. So we can define these segments where you can say this is 0 or 1, depending on whether the segment is chosen or not, right? And all possible patterns of this antenna shape obviously come from some combination of values on this matrix. So what I really need is just a way of saying, if I have something like this, then how can I tell you the goodness of this antenna? And maybe you can do it somehow. There's some techniques for doing that through simulation. And they did this, and they came up with these absolutely bizarre antennas. Nobody in their right mind would design it that way. But guess what? It works. It works very well, and works much better than any human designer could actually design it, because it did things that nobody thought should be done. Okay, it's all completely backwards, but it works. So that's one of the kind of grand successes of this kind of approach. There are many other techniques, and again, I won't go into them in great detail, mainly because I don't know them, but I'm sure you can find out. Okay, so I'm just going to take a pause and say, okay, so we've now covered essentially everything that I want to talk about optimization, and I'll try and sum it up in just a few sentences. So optimization basically says I have some system, and I want to find the knob settings such that it's some values optimized, some objective function is optimized, minimized, or maximized. Knob settings may be even paths like these. And we looked at essentially two things, where the system is linear, the system is not linear. The system is linear. Again, we have two choices. Either it has integer constraints or it doesn't. If it doesn't have integer constraints, and it's linear, life is great. We write out the stuff, and we can, many problems turn out to be modeled in this way. We put it into a solver, and we get a nice solution. If it has integer constraints, things are not so great. We have to be careful about the problem growing too fast. But again, if we are lucky and it's totally unimodular, life is great. Otherwise, we have to do some heuristics. If it's nonlinear, we have, again, if we only have equality constraints, then we can do Lagrangian optimization, assuming the function is nice and smooth and continuous and twice differentiable. And if you have inequality constraints, and the inequality constraints are linear, we can use Kkt conditions, and again, that works out. If all else fails, you have hill climbing. But when you do hill climbing, try to do taboo search, try to do shotgun approaches, and maybe you can try simulated annealing. And if everything else fails, you can always try genetic algorithms. Why not? And then there's a whole other things as well. You have something called ANT algorithms and B algorithms, and I don't know what else out there. If you look it up, there are many other heuristic approaches. They all have the same problem. They work some of the time, and when they don't work, we don't know why they don't work. They just don't work. So you can spend a lot of time doing this. And about a couple of years back, I talked to one of my colleagues in the C&O department, and I said, all right, I have a problem that is not nice and clean. What do I do? He says, there are no guidelines. You just try something. If it works, okay. If it doesn't work, try something else. As far as I can make out, even the optimization people don't really have well-defined guidelines as to which approach to take. I may be wrong. I'd be happy to be corrected, but as far as I know, that's what it is. You say, okay, well, why don't you try ANT algorithm? Why don't you try this? Why don't you try that? And you just see what works. So that's the way it is. Okay, stop here, and then Tuesday we'll continue with probability. And the lecture notes for that are online. Thank you.